Okay. See, it is. So we are dealing with the black body radiations, isn't it? So whenever we consider a black body radiation, we consider a cubical vessel in which the black body is being allowed to pass through. And let us imagine that it is confined. The black body radiations are confined within a cubical box like this, okay, with the side of length A, okay, equal length as a cube. And imagine that this is a black body cavity. Okay. Having uniform sides of length A along all the X, Y, and Z direction. And let's assume that the black body container that we have taken, or the cavity that we have taken, is a non-conductive wall. Means it's not allowing the radiations to further pass through it, penetrate, and or through escape and to go out. Okay, that means it is a non-conductive wall. Okay, means the black body radiations are confined within this black body cavity. Okay, and let's assume that this black body's cavity is starting from the X is equal to 0 and X is equal to A. This is a dimension, A being the length of the cubical cavity. Okay, so imagine that so black body is moving like this, okay, and it will get confined within this place, or it can start from here and it can end over here. This is also one longest wave, isn't it? The longest wave in this particular container can be this way, isn't it? This is the longest wave. Okay? And the next one is, it can be like this, right? So this is with E is equal to 0 and E is equal to 0. These are the state walls, non-conductive walls, and the electric field within this region of electric field, E is equal to 0 to E is equal to 0 on the other side. The black body radiations are allowed to pass. It can take the form of this wave as a full one wave, okay? Or if it's a proper wave, we can say this is a proper wave, isn't it? Okay, this will be a proper wave, and it can be wave pattern like this also. Like this, it goes on. The number of waves can. So you know that the wave will have a sinusoidal wave will be starting from here to here. Okay. So the maximum one can be this, and this can be a proper wave. It can be a 2-wave and 3-wave like this. Okay. I think Bajab has to mute. If anybody can call him and tell. I'm getting background noise. Those are not muted, please mute it. So I hope this is clear, isn't it? We are taking a black body radiation in a wall, in a container with the dimension of A, and the electric field on both the sides of the wall is 0 because it is getting ended. The black body radiations are just getting ended at the walls with E is equal to 0. These are the electric field, okay? Between the electric field, it is getting 0, okay? Now, Rayleigh and Jean, they tried to calculate first how many mode of radiations, how many modes. You know that there are lots of n number of radiations are there within this black body, but there should be some systematic way of calculating certain things, isn't it? So you need to know what is a mode of radiation and how many modes of radiations are possible within a unit area. Okay, we cannot do anything haphazardly, isn't it? We have to have a systematic way of calculation. So we need to know how many modes of radiations are possible, okay, within a particular average area. Okay, so Rayleigh and Jean, they try to calculate, okay, and they try to calculate how many I'm given the note, so you can read it. How many modes of radiation? This is important. The important key points have to be underlined. How many modes of radiations are possible? Okay, inside a cavity. And once you know the number of modes, then it's easy to calculate the energy which are possible. Means because we understand that the black body radiations are in a vibrational mode. They are vibrating with an energy, with a particular energy. So we need to calculate the average energy of the radiations which are passing within the black body cavity. Okay, so how to do that? We need to first calculate how many modes of radiations. Okay, this one is important. How many modes of radiations are possible? Suppose if there is a running race, you will have to calculate, you will have to know how many people are first running, isn't it? And then you'll have to either do, if it's a marathon, you'll have to calculate the 4 people running together, isn't it? Average of how much the among the 4 person, who is one person can go fast, one person can go slow. Okay, you need to calculate the average. So all 4 people's contribution in a marathon race is important. The same way here also we need to calculate the, first we'll have to know how many modes of radiations are possible within a unit area, and then we'll have to calculate the energy, okay, of the black body radiations within a particular unit area. So first that can be calculated with the standing waves. So take for example a particular wave or another wave and see the pattern of the waves. The pattern of wave can be like this, or the pattern of wave can be like this. Okay, so we all know about the stationary waves. No? In class 12 you must have studied the stationary waves that are between stops and then comes back, okay, and forms a stationary wave. So we are going to use that particular concept, and then we are going to use that concept here also. Okay, now it is I hope this is clear up to this. Okay, okay. So first is, our aim is to calculate how many modes of radiations. Okay, how many modes of radiations are possible. So how to do this? There are many ways. Okay, so first see the wave. Okay, this wave can start from here and can end from here. Okay, so this is the longest wave that is possible, and this is between the distance of x is equal to 0 and x is equal to a, within the electric field of E is equal to 0 and E is equal to 0. Okay, and another possible, this is a main possible wave. Okay, it forms a sinusoidal wave pattern like this here. Okay, so this is between a distance of a. Okay, this distance is x is equal to 0 to a. Okay, at the 2 edges. So this starts, both are ending at the nodal position. Okay, between 0 and 0. Okay, so I can see this one has a is equal to lambda x by, this is a wavelength full. Okay, this is the full wavelength one, and this will be the, so this wave is taking this full distance, but the wavelength is going to be lambda by 2. Okay, so a is equal to lambda x by 2. Okay, the next one, the next possible wave will be, okay, the next, this is 1 into 1 wave. Okay, 1 wave by this one. This is according to the stationary wave equation. In class 12 you can refer it. Okay, for the second wave. Okay, so for the second wave you can take it as, this will be just a is equal to lambda x. Okay, this wave will have a is equal to lambda x. Okay, this will have lambda x by 2, because it's just forming one pattern within this distance of half and another one. Okay, so the total will be divided by 2. And another one, the second wave will have, okay, suppose you have two wave like this. This will become 2 into lambda x by 2. Okay. And if there are 3 wave pattern, okay, this will become 2 lambda x by 2. Okay. If there are 3 waves, okay, small waves, I have to draw it. Okay. So up to this is one wave, up to this is another wave, up to this one is another wave. Okay. If you can make a 3 wave pattern, okay, then this will become 3 lambda x by 2, and it goes on. Okay, the first one was just lambda is equal to x is equal to a. The first one was just a. The second one was lambda x by 2. This one, and this will be 3 lambda x by 2. And if you have 4 waves, it will become 4 lambda x by 2, and so on. Okay, so there can be n number of waves in a particular black body cavity. So we can put it as, I can generalize this equation as A is equal to the number of waves, okay, having the wavelength lambda x by 2, okay, where nx refers to 1, 2, 3, etc. Okay. Now knowing this one, okay, if, and this is what air means, the wave are confined within the black body cavity which are traveling along the x direction. Okay. Now similarly, you cannot say that the waves will be traveling only along x direction. Okay, it may travel along the y direction also, it can travel along the z direction also, it can travel along in between x and y, in between y and z, and that will include the angle. First, let's calculate the waves traveling along x direction. So we will similarly take this concept for all the waves which are traveling along the y direction. The waves can travel along this way also, isn't it? And this way also y, and also in the z direction where you can travel like this also. And they can be in between waves which are traveling between x and y. Okay. So first let us put it for the waves that are traveling along the y direction. Okay. So for the waves traveling along y direction, okay, so write it down. If you're not, that is why in online class now, because we are taking fast, you won't be able to write, and the board also may not be visible very clearly. But later on, I'm streaming now this YouTube. You can slowly go through it, and I is equal to ny lambda y by 2. There is some internet problem again. I hope you all got connected, isn't it? Okay. So I'm making the equation for the waves traveling by waves traveling is the direction. Okay, it's going to be A is equal to n z, okay, lambda z by 2. Okay, so we have generalized this equation. Okay, and apart from the which are traveling exactly along the x, y, and z direction, as I said earlier, there can be wave which can travel in between x, y. Okay, making an angle, isn't it? So let's give an angle value for between x and y.
दोस्त लोग मेम का क्या हो रहा है? लेफ्ट अभी निकल गया, तो आप लोग को इसमें दिक्कत दे रहा है क्या?
There's some internet problem by 9 o'clock onwards. Anyway, let's continue. If you're able to hear also, so I think, no? Later on, I'll try to edit and send it. Okay, just listen. Okay, so let's into the angle factor. Okay, as alpha between x and y, beta as the angle between y and z, and gamma the angle between the z direction and the x-axis. So this equation will get modified. Okay, so imagine that there are waves which are all traveling between the x and y direction. So take all the ones with the angle as cos alpha. Okay, cos factor has to be included with angle. Okay, so for all the waves which are traveling along, including the x and y direction, I will give the equation with the angle. So this is the wave traveling along x direction. Okay, the wave traveling in y direction, I'm going to put it like this. Okay, and for the wave traveling along z direction, how will I represent? If I have color marker pen, it will be better. This will be the wave traveling along the z direction. But we cannot say that they are only traveling along perfectly along x or only y or only z. They can travel along in between the distance. Okay, so yes, so the wave can propagate between this x and z, between z and y, between y and z. Okay, so I'm going to include an angle factor of alpha, beta, and gamma. Okay. Are you not able to hear? Hello?
Network is unstable, so you have to record.
Yes, students, I think the network is very unstable. Okay, I will just finish another few lines, and with this equation we will conclude for today's class. Okay? Just hold on. Okay, I hope you have understood up to this, and I'm taking the angle factor including. Okay, so nx will take up all the waves in between the x and y direction with the angle of alpha. So I will put it as nx as 2a cos alpha by 2. Okay, and then ny, I will put it as 2a. Earlier we had only 2a by 2, na? 2. Yeah, ny will become 2 into a cos beta by 2. nz will become 2a cos gamma by 2. Okay, sorry, not, these are all lambda. 2a by lambda, 2a by lambda, sorry, 2a by lambda. Okay, this cos angles, I'm including it. Okay, I hope you are able to see this. Okay, are you able to see? This is 2a cos alpha, 2a cos beta, 2a cos gamma, including all the angle, all whatever waves that are traveling between the x and y direction. I'm putting it as cos alpha, whatever waves that are traveling between y and the other direction. Okay, I'm putting it as cos beta, whatever wave that is traveling between this direction, cos gamma by lambda. Okay, including all the waves, no, we are including this alpha factors, angle factors also into the equation. Okay, now let us add. Our aim is to find the number of modes. Okay, so how to get the number of modes? We'll have to summarize all the waves that are traveling along the x, y, z, and in between all the angles. Okay, so add up all the equations, add up. Okay, so this is nx, ny, and nz, add up. So squaring this equation and then adding the equation, we are going to write it in this way. Okay. So square this equation and then add up. Okay. Squaring and adding this equation. Okay. So nx square nyz plus nz square. Okay. So squaring this equation will become 2a cos alpha by lambda the whole square plus. Okay. The next equation will become 2a cos beta by lambda the whole square. Okay. Plus 2a cos gamma by lambda the whole square. Okay. Add up this equation. Take the common factor here. What is the common factor? 2a by lambda is coming in all the three things, isn't it? So take up 2a by lambda commonly outside. Okay. So this will become now take 2a by lambda cos square alpha plus cos square beta plus cos square gamma. Okay, you all know cos square alpha cos square plus cos square gamma will become by plus, isn't it? So you are left with on the left hand side, you have n square plus ny square plus nz square is equal